I was going to concentrate on the sort of similarities and differences between the sort of program that Yevgeny has been leading and my own program. But I came to the conclusion that Yevgeny's program would require several books to begin to describe it. And for someone who has been more of a follower than a contributor, to try to squeeze it into 45 minutes was ridiculous. So I'm afraid, be concentrating rather more on the co-class business. However, now, hang on, how do I get to the next? Why is the next thing not working? Oh, well, hang on. I've got for some obscure reason, I can't get on to the next slide. Yes, I have. I'm just not being patient enough. So there we are. Obviously, when he, as I say, he kindly invited me to give a lecture, or to arrange me to be invited to give a lecture in the Newton building about Newton's Principia. I'm still wearing the same tie, which has got, in fact, the extracts from Newton's Principia on it. Now, let's see. Yes. So I think if you're going to try to make some serious contribution to the theory of p groups, really all you have to do is to think about the dihedral groups of order 2 to the n and think about them rather carefully. So what do you see with a dihedral group of 2 to the n? Well, you might see it as an example of a p group with an automorphism of order p that has only p fixed points. Or you might see it as a p group of maximal class. And any of the either of these will, of course, generalize in a way which covers all finite p groups. So you might consider, for example, p groups with an automorphism group of order p to the k that fixes p to the r elements for some fixed p and r. Would be one way of generalizing the first approach. Or the second approach, you can consider p groups of co-class r for any r. The co-class of a p group of order p to the n and class c being defined to be n minus c. So both of these would cover all finite p groups. Now, here's an old theorem of Evgeny's, and if I can just move it aside, I can actually read my own slide. How do I do it? Well, that's not what I wanted to do. Anyway, first of all, so hang on. Yes. So if a finite group has an automorphism of order p with precisely p to the m fixed points, then it has this characteristic subgroup of pm bounded index and class at most HP, where HP is Higman's function as given. So if p equals 2, then p is abelian by small, where small just means that it's pm bounded. Okay, so that is one theorem which comes from the sort of approach of the way Evgeny looks at dihedral groups, and here is an old co-class theorem, which says if P is a finite P group of co-class R, then P has a characteristic subgroup of nilpotency at most 2, or if P equals 2, it's abelian, and of PR bounded index. So if P equals 2, we come essentially to the same conclusion, whichever way we look at it. I shall be using basic structure theorems for P groups of finite co-class. You can't say anything very interesting about groups of bounded co-class without proving really quite tricky theorems. But the basic stuff is now quite old and is covered in this book that Susan Mackay and I wrote, and I shall just use these theorems as I need them. Here are some of my co-workers, organized in a random way by my daughter. I might mention Jacques Titz, his contribution. Well, see, Steve Donkin proved that a pro-P group of finite co-class is p-adic analytic provided that P is greater than 3. And Jacques Tietz invited Steve to Paris, where he showed him how to, using the theory of buildings, how you could cope with the cases P equals 2 and 3, which was a bit discouraging, which was brilliant. But it did mean that the book that Sue and I were supposed to be writing was going to be, we're going to have to explain the theory of buildings, which we were not in a good state to do. But fortunately, the situation was rescued. I hope his name hasn't disappeared altogether, by Anna Shalev, no, it's there, who produced an absolutely brilliant paper, which proved the fundamental conjecture without the theory of buildings, but using very interesting results of Lie algebras and so on and so forth. Now, as a result of the I think the success we've had with co-class theory, we have this vague but plausible aspiration. So you have some property, you have some question. Does every finite P group have some property or other? And we hope to be able to give you some sort of an answer. So first possibility is no, and here's a counterexample, because the co-class theory is sufficiently detailed that we actually construct groups, and we may hope to find a counterexample. Second possibility, we would expect to be able to say that, well, then there are only finitely many counterexamples for P groups of co-class R for fixed P and R, because and the third possible answer is that it wasn't a sensible question, and we expect to be able to produce one of these three answers. And the second of these responses will not necessarily be considered helpful. I mean, it may be fairly obvious that only finitely many of these groups can have co-class R. But anyway, that is our aspiration, to solve all problems in P group theory to some extent. Then we have a less vague but absurd aspiration, which is to classify all finite P groups up to isomorphism. Can this be done? The answer, of course, is no. Of course, it can't. But the central question in current co-class theory aims to prove the existence of such a classification, whatever that means. It's not immediately obvious what is meant by a classification up to isomorphism, but we hope that a classification exists which should allow one to print out, for example, the number of groups of order P to the n and co-class R, and to give power commutator presentations for them in time that is linear in the size of the output. Obviously, the output is drastically exponential in the size of the input, but linear in the size of the output is the best you can hope. So we just print out the order. It'll be a very large number, and it'll take some time before the printer's got to the end of it. But to be able to just print it out, and you want power commutator presentations, they will churn them out very rapidly. However, that is saying that the algorithm exists. But to construct the algorithm in general, and in general it covers almost all cases, would make the number of nanoseconds, say, in the expected lifetime of the universe look very, very small. It is not, I'm not saying we can do it. I'm just saying that there is a classification, and I also have to add the important word perhaps. Now, the basic idea then is that we take the P groups of co-class R, and we first of all we have to exclude a finite set. But apart from the finite set that we've excluded, there are also a finite number of infinite sets where we have a good grip. So and we don't actually have a precise bound to the size of the finite set, though we're not too far from having one. So the first thing to do is to construct the pro-P groups of finite co-class. So a pro-P group of co-class R just meaning the inverse limit of finite P groups of co-class R. For example, If P is 2 and R equals 1, you want a pro2 group of co-class 1. There's only one. You just take the two adducts and extend it by a cyclic group of order 2, split extension, it's multiplication by -1, and there you are. That is the only pro2 group of co-class 1. And the idea extends immediately to odd primes. You take the integers in the pth cyclotomic number field and extend it by a cyclic group of order p, split extension. There you are. There's only one pro-p group, which is only one. So that makes things look rather hopeful. We don't want there to be too many. We do not want there to be too many. However, if I hit, I must see. Yes. Right, now, hang on. Have I? Yes. So, right, a mainline group. So, if we construct the easiest way to construct a finite P group of co-class R then is just to take one of these pro-P groups and divide something out. They are all going to be extensions of a lattice T by a P group that acts finite P group that acts unidiserially on it. And so they're all of that form. We saw for R equals 1 what the form was, and it's similar for arbitrary co-class. You get a lattice T, in other words, a free ZP modular finite rank, and you extend it by a P group. And any quotient of one of these is called a mainline group. And for example, the dihedral groups are mainline groups because you take Z2 colon C2, chop off a normal subgroup of this group, and you've got a dihedral group. So those are the mainline groups. Right, and if G is a finite P group of co-class R and sufficiently large order, there is a unique pro-P group such that G has a normal subgroup with G over M being a mainline group. I'm just trying to know. So now we have succeeded in partitioning the set of groups, finite groups of co-class R, into a finite set, the groups which are too small, and for each pro-P group of finite co-class, of which there are only finitely many, those which have a quotient which is a quotient of that pro-P group and of none other, so that the pro-P groups are used to index these infinite classes. Now, I'm having some trouble in going from one page to the next. I don't know why. Perhaps I'm not. Sorry. Why is that? Yes. Okay. Now, however, there are difficulties. The first dispiriting statistic, and there'll be another one, is Bettina Eich has proved that there are whatever it is 137,299,953,383 pro-3 groups of co-class 4. If you put a naught before that, it's probably a telephone number. But anyway. And most of these will give rise to exponentially many groups G of order 3 to the n and co-class 4. And although we can hope that a finite calculation would give rise to a classification of all those groups, in practice that would be impossible. So we have got a very large number of problems on our hands, each of which we hope has a theoretical solution, which could be calculated if there was enough time in the life of the universe, and there isn't. It's just too difficult. So the tree. So we've seen how the P groups of co-class R that are with finitely many exceptions are associated with pro-P group, and each of these pro-P groups gives rise to a tree. And the tree consists, the vertices of the tree are those P groups of co-class R which have a quotient, which is also a quotient of that space group and of none other. So you have a main line with the tree seems to have been drawn with the root at the bottom, which is reasonable enough, I suppose. So as you go up the main, as you go up the tree, well, the tree goes on forever. It's an inverse limit, and the branches come off as follows. What you're doing is you're taking the vertices of your tree are the groups, and an edge joins a group G to G over gamma n of G, where gamma n is the last non-trivial term of the lower central series. All right, and so that turns these things into a tree. There's a single infinite chain, which and the space group that you're interested in, the pro-p group that you're interested in, is the inverse limit of that infinite chain, and the other groups all come off as branches. And let's say the depth of a vertex or a group is its distance from the main line. So it has to say it has depth k says that if you divide out by the term of the lower central series, which has order p to the k, you're then on the main line. You're then a quotient of the pro p group. Now, in general, the length of the branches is bounded approximately by the distance that they are from the root. So you go up a certain distance, say n, and then the branches at that point can only have length n. However, for p equals 2, you only have branches of length 1. If you take a quaternion or semidihedral group and you just chop off the last term of the lower central series, you have a dihedral group, which is a main line group. So here you've got a very thin tree. There's just a stalk, and at every point there are just two little branches. There's two little twigs coming off. They're called twigs. And for p equals 2, and for any coclass, or for p equals 3 and coclass 1, the depth, or the depth, or if you like, the length of the branches is bounded. It doesn't get bigger as you go further up the tree. And in fact, yes, so that for p equals 2 and r equals 1, it's obviously 1, and also for p equals 3 and r equals 1, the depth is at most 1. But those are not particularly interesting cases. Now we have skeleton groups. How is it then that you're going to construct these branches, these serious branches? Now, here is a very trivial way of constructing groups of class 2. I haven't seen this construction anywhere else, but it's a very obvious and simple construction. You start off with a finite abelian p group for odd p, and we define a wedge A is the obvious way, so that it's generated by pairs A1, A2, with A1 and A2 in capital A, and then you make it linear in both variables, as with a tensor product, and you also divide out by the relation A wedge A, and there you are. So you can define the wedge product in just about exactly the same way you do for vector spaces. And now you take a subgroup of A and a homomorphism from A over B wedge A over B to B, which lifts then to a homomorphism of A wedge A to B. And now we just mess up the multiplication. Well, I was writing the abelian group as additively, but now I'm going to get a multiplicative structure. A1 dot A2 is A1 plus A2 plus a half of F of A1 wedge A2. And it's a complete triviality to see that if F is non-zero, that has replaced A by a group of class 2 on the same set. Okay, so that wasn't very difficult. Now, for odd primes, most p groups of coclass R are class 2 by small. Okay, rather than abelian by small, they're class 2 by small. And this construction, this trivial construction that I've just described, it tells you where the class 2 comes from. You just take your, let's just see yes. So let us suppose for simplicity that our space group is the split extension of T by P. in general, it's a non-split extension, and that's important that you get non-split extensions. It's crucial. However, life is simpler with split extensions, and as far as this is concerned, you don't get any interesting new ideas by taking non-split extensions. And now we take A to be the normal subgroup of R of index K in T, so that the normal subgroups of R that of sufficiently large index are obviously lie in T, and P is acting uniserially on T, and so you just go down to your number of steps and you get to your subgroup A. And now you take a homomorphism from T wedge T to A. And if you take B as a normal subgroup now contained in A of sufficiently of index at most K. What's K? K should have been the yes K. What is that's right? Yes, it's K is the index of A. So you go down K steps, and then you go down another K steps and chop it off, and you could get a homomorphism from the wedge product to the smaller group to make it class 2. So halfway down the group, logarithmically, you get into the derived group of what was just a quotient of T. It was a quotient of T and therefore abelian, but you've twisted it by this construction, so it's now class 2, and those are your skeleton groups. And the problem then is to somehow analyze and cope with these skeleton groups. If the original group is not split, the construction is a bit more complicated, but the complications are not particularly interesting. Now, of course, but basically these twisting homomorphisms just come from homomorphisms of T wedge T to T. You can make, given such a homomorphism, by multiplying it by a suitable power of T, you can make the image go down as far as you like. So that's all you need to worry about. And except with these few cases, if P is 3 and you've got an iterated Reith product of cyclic groups of order 3, or then there is a non-zero homomorphism. You all know what an iterated Reith product is, and my daughter Kay has shown you what it actually looks like. Anyway, if there and in those cases where there aren't any homomorphisms, then the skeleton groups, of course, by definition, are mainline. There's nothing else that they could be. So the number of skeleton groups of order P to the n in the tree is generally speaking exponential in n. That is to say that the tree will branch into will have the valency is going to be something like the dimension yes, the valency is approximately going to be the degree of the subgroup T, its rank. That's not a very precise statement, but when the rank that's roughly speaking what's happening. And obviously, if the valency is going to remain large, then you're going to get exponentially many groups. For example, if P equals 3 in co-class 2, you never get the valency is almost always 1, so you just get a linear number. So we can construct these skeleton groups. We can construct the homomorphisms from T wedge T to T without reasonably well. There are always difficulties here and there, but we've got a pretty good grip on the homomorphisms from T wedge T to T, and we can sort of turn the handle and construct these groups. But it's very difficult to get to decide theoretically when two are isomorphic. If you take two specific ones, you can tell whether they're isomorphic in polynomial time because you've got bounded rank. But it's not so, but to produce a proper analysis of when they're isomorphic so that you can say that you really understand what's going on, it's very difficult. And mistakes occur. So anyway, right. So more dispiriting statistics. It turns out, well, you see, first of all, yes, all but finitely many two groups of co-class 2 have depth at most. Remember, you see the depth, as I say, for p equals 2, the depth is bounded. It's independent of the size, but it only depends on the co-class, and there's your bound. And for odd primes, again, you have a normal subgroup and you divide out by a normal subgroup of bounded order, and you've got a skeleton group. However, for three groups of co-class 4, that says you divide out by a group of order at most 3 to the 11,934, and now you've got a skeleton group. However, while the count of the number of pro-P groups of co-class 3 is just the number that it is, I think that this bound of 3 to the 11,934 is far too big. This formula is a result of a lot. It doesn't is a result of quite a lot of work. And someone said to me, "There's no way that you've got that bound correct. You must have made some mistakes on the way, but it doesn't matter very much." Actually, Sue Mackay, who was my joint author, is extremely good at coping with difficult technical complexities, and no one has actually found a mistake. But still, I think the comment that if there is some slight mistake, it doesn't matter very much is fair enough. That bound is I'm fairly confident far too high. Anyway. So now we want to get some sort of control over this business. So we're looking for symmetries. So first of all, if we take this tree and we delete all vertices of depth greater than t for some fixed t, we just cut it off at depth t. Now for k large enough, as you go up the tree, eventually it becomes periodic. Okay, and because after a while it becomes periodic, you can therefore get a finite description of the whole setup. And not only can you get a finite description, but you can describe all these groups with a finite number of power commutator presentations, which are with a parameter. So if you take the case p equals 2 and r equals 1, you can all of you immediately write down a single parametrized presentation of the dihedral groups, similarly for the semi-dihedral and the generalized quaternion. It's very easy, and you can do that in general. The fact that this does become periodic was first proved by Marcus du Sautoy using zeta functions and model theory, which was really very exciting. But it is the nature of that kind of proof built into its very core that prevents it from giving explicit bounds. But Bettina Reich and I have a homological proof, which I quite like, and so we do begin to get explicit bounds. However, there we are. Now, so for p equals 2 now, we have proved the existence of our finite classification for any co-class. There are. It's completely proved. So if these classifications exist, you say, well, let's see them. Well, for p equals 2 and r equals 1, it's sort of for first year group theory. You just get these three groups. P equals 2 and r equals 2, it gets a bit trickier. And the first attempts at this got it wrong. P equals 2 and r equals 3 has not, as far as I'm aware, yet been completed. we know what the answer is from computer calculations, morally speaking, but to actually prove that it's correct, I think the proof is still incomplete. And when I say the case I equals 4 is surely out of reach, that's perhaps a bit pessimistic. But that's where you're going to get stuck, somewhere around r equals 3, r equals 4. It just gets too damn complicated. And so, however, let's not worry about that and look for symmetries of a second kind, where we're going deeper and deeper into the tree, further and further from the main line. Now, so the question is, what sort of symmetries would enable us to conquer the question of when you've got branches of increasing length as they leave the tree from further and further up, they get longer and longer. What kind of symmetry is going to help you? And the idea is as follows. You can classify the tree, as I've already stated. If you up to a certain, if you shave the branches off at a certain depth, and if you organize that depth to be big enough, then the hope is this: that you take a vertex which is greater than that distance from the main line. And if D is the rank of the translation subgroup, the abelian group in your space group, if D is the rank of T, then if you've got this vertex which is within in a suitable distance of a main line, so you classify, you understand that, and you now take another vertex, I'm sorry, which is deeper than that, but no, I'm sorry, let me get this right. You've gone to a suitable depth, so that when you take a vertex at this depth, you can go D steps up. It takes its D step ancestor, and so now when you take D step ancestor, that's got to have to be a group which is bigger by a factor of p to the D. Now you move from that vertex in some unspecified way down towards the root of the tree, in the direction of the root, but keeping the same distance. And when you go down in that way, the groups get smaller by a factor of p, roughly speaking, every time you step down. So you go up towards the branch, up the branch, and then parallel to and then you move down keeping parallel to the trunk, and you hope to find a group there which should have the same order, and you hope that it's got the subtree which is rooted at these 2 points are isomorphic. So that once you have constructed the groups to a certain depth, you can construct the tree step by step, starting off at the bottom, and you're getting these longer and longer branches, and when you're at the edge of the depth to which you've shaved it with your first shaving, you take this group, you then find it's got a twin which is further back, and you've already produced the tree which is which has that as its root, and you just copy that root. You just copy that tree into the group you first thought of, so that in this way, once you've constructed the tree to a suitable depth, the construction of the rest of the tree is a triviality. You're just copying what you've got before. So, of course, you're copying it further down because the groups have got to get bigger. But you've got the first kind of classification it takes you along, and the second one takes you down, and so you can describe them all with a finite number of things. It's a conjecture or hope that such a construction exists, and that it behaves itself, and that we can get to understand it. and it seems to work perfectly well as far as that we can more or less deal with the three groups of co-class 2. Let me just say, first of all, that it would be impossible to classify the 7 groups of maximal class, the 5 groups of second maximal class, or the 3 groups of third maximal class, just because it's too bloody complicated. It's not a lack of lack of ideas. It's rather like classifying the groups of order P to the n. That there comes a point where you say, "Well, I'm bored with this." You have to hope that someone is going to get a nice computer program that's going to do it for you. But all kinds of really quite interesting features do turn up, but they're very technical. And unless you're really prepared to spend a lot of time thinking about the minutiae of the detail, you're not going to get there. So anyway, yes, right. So that is in a sense, you see, we're claiming to classify all finite p groups, and as you can see, there are sort of obstructions to final success. So what next? Well, I think actually there is quite an interesting problem. Which I would just like to mention very briefly. I've got a couple of seconds left, which is not something I've put on the slide. If you take one of these profinite p groups of co-class R, call it G, then there exists an integer I, with a property that if you take a different pro-p group H, and if G over gamma Ig is isomorphic to H over gamma IH, then G is isomorphic to H. That is to say, G is determined as an infinite pro-p group by its quotient by some finite term of the lower central series. That determines it. It's clear that not all pro-p groups can have this property, because there are uncountably many of the finitely generated pro-p groups. So it's a rather rare property, but I don't know what other groups have this property. Perhaps the Nottingham group, for example, does that have this property? And if it doesn't have that property, it might still have the property that if you take a pro-p group H with the property that modulo some sufficiently deep term such that for some sufficiently large I, your new group G over gamma Ig is isomorphic to n over gamma In, where n is the Nottingham group. Then even if it's not isomorphic to the Nottingham group, it might still have the same pattern of lower central factors. That is to say, gamma I over gamma I plus 1, you get what you get. You get a CP cross CP, and then you get P minus 1 CPs, and then you get a CP cross CP. And that pattern of lower central series might remain the same. You get phenomena of this kind, those are settled P groups, with the P groups of maximal class, well, of fixed co-class. If you take a group if you take a group of a P group P, and if P over gamma IP is of co-class R, and if I is big enough, then P itself is of co-class R. The co-class is already determined by its quotient modulo gamma Ig for some I. And I wonder whether this sort of phenomenon, which we call being settled, extends to P groups of other kinds, and indeed perhaps groups of other kind, but let's say P groups of other kind, that these groups are determined in some sense by their quotients with a sufficiently low term of the lower central series. I just don't know. Anyway, there are various other things. So co-class theory, yes, it has sort of leaked off into semigroups and associative algebras, but it doesn't seem to work well for Lie algebras. And you can improve the bounds. And the integral cohomology would be quite interesting, and so on and so forth. But I'm waffling. I'm afraid. But anyway, so anyway, thanks to everyone, and it's been great fun to be as it were in Lincoln again. I've really enjoyed my time there, and good luck to everyone. And Evgeny, I'm sure you'll have an extremely productive retirement. Thank you.